Okay, we're going to start off this video looking at a voltaic cell. And the general idea of that is we're looking at just potential energy, voltage, potential energy of different elements having an attraction for electrons. So you can kind of think of it from the standpoint of electronegativity, like Zeph, like atoms being able to attract electrons better than others. So the one we're going to look at here is we're going to call this picture time. We're going to draw two beakers, beaker one, and I will apologize ahead of time for my drawings. They're terrible, I know it. So we got two beakers, and we have these plates within them. This is like a piece of metal within there. Specifically, this metal plate is made of zinc, and this metal plate is made of copper. And then they are attached by a wire, a non-reacting wire that bridges over these two plates. Now within this solution is a zinc solution. So it's aqueous 2+, and it happens to be 1 molarity. That's just for consistency's sake, 1 molarity. Over here, you have a copper solution, which is 2, or copper 2, excuse me, also 1 molarity. This is a meter that measures the voltage of the system. So you've got some decimal number in here. We're going to try to figure out what that number is. Now this is a circuit, and right now it's not complete. So we have to have what's called a salt bridge. There's a couple different ways you can do this. This is one. This is a salt bridge which is saturated with, I'm going to write it below just so it's a little more clear, of sodium nitrate. Now you may remember what we talked about before in regards to reactions is group 1 metals, they don't react well at all with anything. They're in solution, they just hang out there and do nothing. Group 1 sodium ions, so remember that, sodium plus 1. And then nitrate is NO3 minus 1. Nitrates also don't react well. They're just kind of there in solution, not really contributing at all to what's going on. Okay, so this can kind of flow back and forth as it wants to, this sodium and nitrate solution. It's not affecting anything. The only thing it does affect is the charge. So its ability to move back and forth is really going to be dictated by what's going on with these two solutions and the plates, of course. So we'll get into that as we're kind of moving along. Now, what we're trying to look at is, well, what's going to happen? One of these plates, and we can kind of talk about this now, is going to have electrons moving from one side to the other. They're going to be flowing from one side to the other. And the actual side that it is happening on is from zinc to copper. So these ions, these copper ions, just think about it like in nature. I mean, you see copper metal a lot because it's fairly stable stuff. Zinc also could be considered fairly stable, but it's not as stable as copper. So the copper is more electron hungry, if you will, than the zinc. So the electrons are being pulled from the zinc side, specifically the metal plate, and they're moving over to the copper plate. So what we'll have here is electrons moving, and this is the flow of electrons, which creates a voltage. So these electrons are moving from the zinc over to the copper plate. And they're kind of like gathering on the outside. So there's like a charge on this outside. Now they're not just sitting here. This copper metal, or excuse me, ions, copper 2+, is attracted over because positives and negatives, and they are picking up these electrons. And as it turns from copper 2+ to copper 0, it starts to plate out onto the outside of the plate. And you would actually be able to notice this because it'll kind of start looking fuzzy and start seeing metallic copper forming on the outside of this plate. Now just the opposite's happening over here on this side. Because the electrons are leaving the metal plate, this is kind of like dissolving, or it looks like it's breaking apart. And you start to see some holes on the outside, and it just looks like it's degrading, corroding. And what's going into solution is zinc 2 plus. So we have two different things going on in these two beakers. So we have this going on over here. Now, one last thing is, because I have positives leaving this solution to create this circuit, we have to have this coming into play. It's not reacting, it's just taking the place of these positives leaving. So going into solution over here are sodium ions, just to compensate for the loss of the positive ions over here, and then just the opposite over here to balance out the negative, or the positives coming in, the negatives are pulled into this solution over there. Again, to complete the bridge. No reaction taking place there whatsoever. So to take a look at the half reactions that are actually happening here, you have zinc solid that is corroding and is forming zinc ions. And I'll just put aqueous down just so we can see it. And also within that is you have 2 electrons being lost. So again, the idea of losing electrons, this is an oxidation reaction. Oxidation reaction. And the opposite is going on with the copper. The copper is sitting over here, copper 2 plus, and it is attracting electrons. It's gaining electrons and forming copper metal. And therefore that is called reduction. And I'll go ahead and make sure I put the little symbols on this just so we're clear. And there you have it. So I mentioned there's a voltage thing going on here as well. Let's talk about specifically what that voltage would be. Well, just to define what a volt is. A volt, which you've probably heard before, by definition, it is 1 joule of energy based on the charge of the electrons, and it's called a coulomb. So the coulomb. So the energy per coulomb, or the charge of it. And again, the idea of it is, what we're looking at here is the potential energy based on the electron charge. We're just restating this differently. Same thing. Just to define it, what is the charge? A 1 electron charge is equal to something very, very small, 1.60 times 10 to the negative 19 coulombs. So it's very, very small based on electron charge. But of course, we're looking at the energy incomparable, and then it starts to scale up from there. So if we want to figure out exactly what's going on with this reaction, we have to look at how these are going to relate. And boy, this is getting complicated. There's a lot going on here, but you kind of get it once you've seen it enough times. The reaction, it looks more complicated than this, so just work with me on this. It's based on the charge difference, the charge of the cell. It's the comparison, or the difference, of what's going on at the cell that has reduction, and I'm going to put a space here. What's going on for the reduction of the other cells. So the difference in the reduction potentials of these two cells. And at the moment, I'm sure I hear it loud and clear, huh? Okay, let's back up a step. There's something I didn't mention before, and we have to talk about it. You've probably heard of cathodes and anodes. It's just like this electricity concept. And cathodes is a location of a cell in which electrons are being gained. Or I'm sorry, the cathode is a location, the cathode's location where electrons are being gained, reduction. So let me go ahead and label these, and we'll talk a little bit more here. So I can tell you right now, electrons are being gained over here. We can see the electrons gathering, and I'm going to write down reduction. I'll just put red for reduction. So if I can do that, then this area here is losing electrons. Electrons are being lost, they're going away. I can therefore say this is oxidation, right? Leo says GR, lose electrons, oxidation, gain electrons, reduction. And oxidation happens at the anode. And reduction happens at the cathode. And this is just something you have to memorize. There's two different ways you can memorize this. The way one easy way to do it is vowel, vowel, and consonant, consonant. Very easy to remember that. The other way, I always remembered it, is reduction and cat. I personally don't like cats very much, so reduce the cats. That works perfect for me. Reduce the cats. Okay, so as far as looking at this, whenever you look at one of these equations, you have to do it based on reduction. So when you look in your book, it happens to be Appendix E. If you look in your book in Appendix E, you'll find a whole bunch of reduction potentials. So I look up what it is for copper 2+, and I look up what it is for zinc 2+. And reduction again is gaining electrons. So when I look these two up, what I will find is I have some values for it. And let me go ahead and let me pause on that for a second and finish this equation, and then I'll come back around to it. So the way this always works every single time is cathode minus anode. Every single time. Cathode, which is the more positive value is going to be the cathode. And then the anode is going to be the second value. But remember, they're always putting reduction potential values into this equation. So when I look these up, I look up for the cathode. Well, whose the cathode is this one? So copper's value comes first. When I look in the book, I will see that copper's value is 0.337, and it's positive. And I will subtract the reduction potential value that I find for the anode, which is zinc. When I look that up in the back of the book, Appendix E, I will see that it is this value. And of course, when I do the math, you will get a value of 1.10 total volts, a positive value. Now, if it's a positive value, it means it works. So right now we're just kind of talking like, what if we actually did this? The fact that its value is positive tells me that this process, what we actually drew up here, is really going to happen. That process is actually going to go. And that's the whole thing there. Easy enough. So we'll try another one here as we're going through the rest of the problems.